So now that we have the basic sort of notions that we need. So the first kind of question, like I said, is we would like to know which node in the network is important, right? So we want to basically be able to rank the nodes from the most important to the least important. So this is actually, we can formalize this as a mathematical function. We can say that what we have is a graph with n nodes, and what I want to do is I want to learn this mapping. Okay, so mapping from, so this function will be called a centrality. Centrality will be a different kind, as you'll see. So this is just some importance function, or a ranking function, which will assign a real value. Okay, so this is the real number. So you take the vertices and you map, each vertex will get some score. So the highest score vertex will be the more important one, and so on. So okay, fine. So the question is, how can we define these scores? So the simplest notion is that of degree. Obviously, if a node has high degree, it is an important node, right? So that's called the degree centrality. So that's the simplest kind of ranking we can do. Since we have these numbers, we can just say, here's the highest degree node, the next one, the next one, the next one. So that will be the degree centrality. So the higher the degree, the more important you are, which kind of makes sense in many different applications. Then we come to a notion of eccentricity centrality. So eccentricity, this is the reciprocal of the eccentricity. That means the smaller the distance to other people, the more important you are. Like in the example of that center node, right? The nodes that are in the center of the network, in the middle of the network, they are the important nodes. Otherwise, you're on the periphery. You're sort of far away. So in Delhi, right, the heart of Delhi would be the important part of Delhi in the sense of connectivity. And if you're living in the outskirts, obviously you're a peripheral locality. So from a transportation point of view, that would be the sort of the importance. So the closer to the center you are, the more important you are. So what you're doing here is you're taking the inverse of the maximum distance, right? So that's called the eccentricity centrality. Now, contrast this with another notion. So we can take that and we can talk about closeness centrality. And this is 1 over the sum of the distances. Okay, so you don't take the max. You say for a given node, we want to know, can you, so you have to minimize, right? So to get a high value for the score, you have to minimize the sum of the distances to everyone else. Okay. Here you just have to you have to minimize the maximum distance, but here is the sum of the distances. Okay. So now, what is the difference between these two types of centralities? So actually, these two really are one of the key ways of what we call facility location. Okay. So they actually are guidelines on how to locate things. So for example, this is useful in locating a hospital. Okay, so what do you want to do in a hospital? It's people should be able to get to the hospital quickly, and no one should have an unnecessarily long delay to get to the hospital. Right? So what you're doing is you're minimizing the maximum distance. So you say, if I want to put a new hospital in some location, I should choose the center so that anyone can get to the hospital relatively quickly. Okay, there's no long delay to get to the hospital. Doesn't matter whether you're rich or poor. I want everyone to be able to come to the hospital, let's say within half an hour, right? So that's, you would try to, find a location that has a high centrality for the eccentricity. Whereas the closeness, it's sort of like, it's for, if you want to put a new, restaurant, I don't know, Pizza Hut or some other restaurant, for example, you want to put that restaurant somewhere. You don't care if for some, for one person it takes 5 hours to come to that restaurant. But what you want to do is you want to basically make sure that many people can come to you. Right? The sum of the distances should be minimized, but we don't really care about the max too much, right? So these are sort of very useful notions to actually. So they have real value. That they actually tell us something about how to structure the network. But in this case, of course, we're doing the reverse. So you can use it for facility management and location. But here we're just saying that in terms of which are the important nodes, we can define them in terms of the maximum or the sum. Sum is very close to the average anyway. So you can think of this as you're minimizing the average distance to other nodes. So of course, these are all very simple notions. But here's another very interesting one. It's called betweenness centrality. Again, one of the key sort of concepts in understanding network connectivity and who is important. But this one is actually very interesting because so far you're looking at the shortest paths to other people, right? So from this node to other people, what was my shortest path, whether the max or the sum. But this one, it basically says that, in a nutshell, it's like if there's a node here, okay, so let's say there's a node here, and there's the rest of the graph, right? So there are nodes here, there are nodes here, node here, node here, node here, node here. So and I've sort of drawn them as if they are like two wings of the thing, but generally whatever the graph structure is there. The question you want to know is how many shortest paths go through that red node. So in other words, you have to compute the shortest path. So it's possible that for example these two, they might be a direct link. Okay. So this red node, and so let's call this node V. So V has no role to play, right? So in the shortest path, you can completely bypass V. So V is not central, it's not between those two. Whereas, let's say this one goes through here, that means V is now playing a key sort of role in that shortest path. So how many shortest paths there are, such that V plays a role and whatever the network structure happens to be. So if your network is like this, we basically look at, for how many shortest paths go through V, that would be the ratio on top. Okay, so you look at all so the idea is that you look at all other pairs. So Vi is your node of interest. Jk are any two other vertices. Okay, so pick Vj and Vk, and you basically compute the number of shortest paths between J and K that go through Vi. Okay, and you divide that by the number of shortest paths between J and K with or without Vi. So that ratio says that among all the shortest paths, among all the possible pairs of vertices, okay, this fraction goes through you. The rest could be some other shortest paths. So the more you are between, that is, the more you are on the shortest path, the more important you are. That means, obviously this makes a lot of sense for logistics and transportation, right? That means these are, maybe the key road segments or the key, intersections, where a lot of the traffic from one end of Delhi going to the other end of Delhi, it has to go through that. But now we have ring roads and outer ring roads, so maybe but that will still be taken into account, that how central you are, how between you are. So you can formalize that. So I will not really go into the the full. I think it's simple to understand that actually all you're doing is you're picking just pairs of nodes, and we are finding the shortest path between all of them, and then we see what fraction goes through Vi, what fraction is there in general, and then so that's basically summed over all J and all K. So that's the centrality for a given node. And so the more between you are, the more important you are. And this is also very important for, you could say for strategic, right? So let me give you another example. So this would be in the case of, let's say, computer networks, right? So security, right? So if I'm a bad guy, right, I want to attack a network, these are the nodes I'm going to basically try to disrupt, right? So do a denial of service attack on that. So that will basically clog and block all the traffic going through, So that means two parts of the world or two parts of the country can no longer communicate with each other. That means the whole network has basically come to a standstill. So these are, again, so then what you do is you do the counter attack, right? So it would be okay. If I had to, I have a physical network and I have to prevent these kinds of, disruptions from happening, what should I do? That means I should make sure that there are, replicators, you can replicate these nodes and the capabilities in other parts so that it's not all focused on one. You can do this for electrical grids also, right? So you do grid supply, and sometimes you have these rolling blackouts, right? So basically one part of the country goes dark, another goes dark, another goes dark. Again, it's a cascade. And the question is that something failed, and that causes this whole ripple effect. So what should you do? You must make sure that these that the point where these starts, that means there must have been some weakness in the system, in the network, that is basically allowing this to propagate. So these are basically now counterattacks. So you can do design to prevent attacks to computer networks, electric grids, other types of, So there are both positive and negative aspects, but whichever way you look at it, the positive aspect would be, in a disaster recovery scenario, right? These are the key things, and you should make sure that your supply gets to these points very quickly, right? And then you can distribute it to the rest of the people very quickly. So again, depending on the application, this is what you want to understand is that betweenness plays a key role in analyzing the structure. Just from a purely structural point of view, these are the important nodes in my graph. So like in this example, this is that same toy example. I have basically listed out, some of the nodes. So it turns out that the highest one is V5. Okay. So if you look at the betweenness, V5 turns out to be the most critical node in this network because of the role it is playing in terms of the shortest paths. So it's a little bit higher than, for example, V2. So V2 is also important. But anyway, so there are different notions. Again, you can combine them in different ways, but they're all just saying that with respect to a certain notion, right, how important you are. And then, the other side of this is, depending on the application, let's say you identify the important nodes. Then the other question would be, why are they important, right? And so that comes into, this is a place where computer science can make a difference. You work with the social scientists, you work with the biologists, you work with the, transportation, mechanical engineers, civil engineers, and you work with them to really understand, what is the meaning for this. So in a network, you have these kinds of things, and we collaborate with other scientists to figure out what does it mean in their, from their point of view. Because computationally, we can do all kinds of analysis, but the key insight is really if we can close the loop. Right? I can take a data, I can extract all kinds of interesting things, but then as a computer scientist, I don't have the capability or the expertise to really take it to the next step. So then we need to have domain experts to take that data, work with them to then gain insight. So that's one of the key challenges, is to work with someone to really make sense of it. All right, so now we're going to actually switch gears, and we're going to talk about one of the fundamental notions. And for this, I need a little bit, it's like a very direct jump into linear algebra. So this is our first encounter with the Markov chain notion. So maybe I need to, what I'm going to do is I'm going to switch slides, because I have some other slides for this to illustrate the idea. Then I'll come back and continue from here. So let me give the intuition first. Okay? So this is a notion of using a walk, okay? A random walk essentially, to figure out what is important and what is not important. And the basic idea is that what we want to do is we want to compute something called the prestige. Okay? The prestige will be something very similar to the Pagerank, right? So the Google Pagerank, which is the importance of a page. So when you click on a search result in a keywords, they're going to display the pages in PageRank order. So that PageRank value is very closely related to this notion of prestige. So they call it the authority score. Okay, so how authoritative you are, but it's the same basic idea. And this, by the way, predates Google's PageRank by at least 30 years. Okay, this work was done in the 70s by social scientists. Obviously, they were looking at small, social networks, maybe 30 people, 40 people. So they were not doing it at the web scale, but they were looking at this notion of prestige, right? So prestige, that is how prestigious you are. So what is the fundamental notion here? The fundamental notion is a recursive definition. Okay. So let's assume that I can give, so let's say in this room, what we can do is we can give each person a value of 1. Okay, so we all start out with the same value. Now we let the structure determine how important a node is in terms of the information flow. So it's actually a very it's kind of like a flow of this weight, right? So you basically say the following. You say, okay, I have the score of 1, and let's say I pick a few friends of mine, in fact all the friends of mine in this room, and I give them my score. Okay. So if I have high prestige, they get higher prestige, because they can take the scores of the neighbors, and they're basically going to sum it up. Okay, so every node will do the same thing. So it's a recursive definition. Okay, it says that the prestige of a node V depends on the adjacency. So this is where the adjacency matrix comes into play. So you look at all other neighbors, right? All the neighbors U. Look at the edge from U to V, and look at the prestige of U. Okay, so you're defining my prestige in terms of the prestige of my friends, okay, or my neighbors. So this is the basic definition. So how do you compute this? The way you actually compute this is you do iterative. Okay, this is an example of an iterative matrix operation, where at every step what happens is that you start out with equal weights, everyone has the same prestige, but what will happen is that a node, if everyone has equal prestige, the node that has higher neighbors will get more incoming weights coming in. So in the next step, their prestige will go up because they'll borrow from their neighbors. So the more the degree, of course, the more you'll borrow from your neighbors, and your prestige will go up. And then you repeat. So now my prestige has gone up, someone else's prestige has gone up, and you keep on repeating this. Okay? And then the question is, what happens? Interestingly, one can show that this is actually classically more or less like a Markov chain. Okay, not exactly a Markov chain because it's not purely probabilistic. So we'll make it Markov chain later, but it's essentially it's called the iterative approach to computing the prestige. So let me illustrate that, and then I'll come back here. Okay, so let's make it more Markovian, right? So let's actually talk about Pagerank, because prestige, as I said, is very closely related to Pagerank. So this is exactly sort of illustrating that idea that, now in the context of web pages, of course, right? Because you want to rank the web pages. You want to basically know which web pages are important. And you say, okay, if I am important, if other important pages or other good pages point to me, right? So that's the basic notion, that there is a hyperlink from one page to another page. And this page is a very good page, right, very authoritative page. Then my rank should go up because many good pages are referring to me. So that's essentially the basic idea here. So that's this. So in terms of the actual computation, we have, so we define it as follows. So supposing there is a graph like this, right? So we say that, we define something called the page rank of a page, right? So it's just a score. Because a PR of a vertex U is the page rank of vertex U. And the k plus 1 tells you the step. Okay, so which step I am in. Initially, everyone has equal page rank. And in step 2, it will change. In step 3, it will change, and so on. Now, we have done one thing here. And this notation is a bit different from the other thing I've been showing. But this is where we make it a Markov property, that for any vertex V, let's look at this notion of V2. Okay? Now V2, actually not very interesting, so I'm going to come back to this. Okay, let's look at V4. Now V4 has one incoming edge, right? So it, 2. So that means it will inherit, or it will get the page rank value from V1 and V2, okay, because they can contribute to V4. And on the other hand, V4 has 2 outgoing edges, right? So the first thing to make it into a Markov chain is to make a probability vector. We say that actually V4 has 2 neighbors, and it's kind of like I have limited amount of funds, right? I have only limited amount of prestige or a limited amount of authority. And in this case, because my out degree is 2, right? There are 2 outgoing edges. I'm not going to distinguish between them. I'm just going to say 50% goes to one, 50% goes to the other. Because I have a budget of 100%. I cannot exceed that budget. So so what we do is we divide by your outgoing neighbors. Okay? So you divide by your out degree. This is the main. This is the main. This is the main. So this makes it a probability. Okay, so it's a probabilistic notion that I can only contribute 50%, 50%, or in the if I had more neighbors, supposing I had 3 outgoing edges, it would be 33%. One third, one third, one third. So you divide up equally, but you have to divide by your out degree. So this is what makes it a Markov chain. So you divide by out degree. So what that means is that it becomes a probability vector. Okay. So the scores basically they add up to 1, and I can only give that fraction of my score to someone else. And so basically the same thing as before. It's going to be the page rank of my neighbors, okay, but divided by my out degree. And so that makes it a Markov chain. So for example, initially, I will give everyone actually, in this case, equal score, 1/4, 1/4. So there are 4 nodes. I'll say initially they're all equally divided among them. Okay, you get 1/4 of the score. So let's see now what happens in the next step. So I want to now update this information, right? So the next step is, so I want to compute now, so this is your starting point. Everyone had equal page rank. So in step 1, what should happen? Okay, so let's compute that for V1. So let's see. So for V1, we have, so this guy has a score of 0.25, right? It has to contribute the 2.5, half of it to this guy, half of it to that guy, right? So it technically should be 125. I'm not, I'm just doing two digits of precision. So 125 and 125 would have added up to 0.25. But I'm just showing you the first 2 digits. So this will contribute half here, half here. V3 on the other hand has to contribute everything to V1 because there's only one outgoing edge. So the total score here that's coming in is how much? Just we add them up. So it will be 0.37. Okay, that will be the new score for V1. And then you repeat the whole thing. So this is actually this thing can happen simultaneously. Right? So it's actually very easy to parallelize in that sense. That every node can be doing this computation at the same time. It's a simultaneous update of all the nodes using the previous values. So you use the old values to get a new score, okay? And every node does it at the same time. So in fact, all 4 of them update them, and this is what you get in iteration 1. So this is called a lockstep, processing. And so it's an iterative process. Okay, there's iteration 0, iteration 1, iteration 2. But every time, all the nodes are locally computing this because they just have to look at your incoming edges and simply add up the total score that's coming in. Now the interesting thing is what happens if you keep on repeating this. And this is where the matrix algebra, there's a very nice theory behind all this, which I'll get to in a minute. So you say, okay, let's repeat. Right? So let's repeat. What happens next? So iteration 2, I update. Iteration 3, I update. Iteration 4, I update. Iteration 5, I update. And now you start noticing something. What do you notice? It's very similar, right? It's not changing, right? So 0.39, 0.39, 0.19, 0.19, 0.29, okay, there's still some, leeway here, 0.11, 0.13. But essentially one can prove, okay, this is a very nice, you can use the Markov chain, so this is actually a transition matrix, okay, so you're jumping from one state to another state with a certain probability. One can show that this will actually always converge to a unique solution. So in fact, it is actually irrelevant how I start. Okay, I could have given this 0.5, 0.5, 0.5, 0.5, 100, 100, 100, 100. I mean, I'm talking about the actual fraction would not change. Okay, But obviously, we start from 100, that you have to keep on. What we want to ensure in the end is that the whole thing must add up to 1. Okay. Sorry, no, not 1 second. So, no, sorry, it has to be a unit vector. Sorry, it has to be a unit vector. So one can show that this actually converges to the dominant eigenvector. Okay. So this Pagerank is actually a dominant eigenvector computation, and this converges, and it converges very fast. Okay. So the point is that even in a large network, like a web scale network, it will not take very many steps to converge this kind of closeness. So this is called the dominant eigenvector. Okay, so this is actually a classic matrix vector multiplication problem. All you're doing is you're repeatedly multiplying by the Markov, the transition matrix at each step, and you'll get the answer. So I'll come back to that. So that's the key. That's the key insight, that you basically reach what is called as a fixed point or a convergence, and that's your Pagerank solution. So there are lots of details which I'll go over, but this is the key idea, that all we're doing is we are repeatedly doing the same exercise, the same updation over and over again, and the thing converges. One can guarantee that it will always converge. It will always converge to the same value. You cannot have two different solutions. It will always be the same solution.
Excuse me, sir.
Yeah.
Sir, in the scenarios of offline, if we have a dynamic network, means online, what will be the scenario?
The dynamic is the interesting part. So, question is, how does Google do this, right?
Yeah.
So now Google has to remember, Google has to do this on the web scale. So we're talking about billions of pages, right? So Google is not going to recompute the page rank every time. So I don't know what their frequency is. They might do it every night, or they might do it every week. Right? So the idea is that you do a batch. And you don't also recompute everything from scratch. What you do is you look at the changes, and then you can do a quick update. So you want to basically be able to approximate. So in other words, you don't have to get the exact value. You just have to get the ordering right. So in practice, what you should do is you do an incremental update. So as the graph changes, things come in, things go. The graph is growing, new nodes are coming in. So the idea is that you have to come up with techniques to handle those kind of scenarios. But the basic computation is still the same. That it's just the frequency at which you do it. So normally Google will do definitely, perhaps every night, or most likely every week they might update. Okay. Ultimately it doesn't really matter, because even if things are changing rapidly, are you really interested in that part, right? You're probably interested in the more popular content, and that doesn't change, in terms of the pages, right? So anyway, that's how it is. All right, so let's go back. So coming back to this, so let me come back a little bit, so because as I said, the Pagerank is actually built upon on this prestige. So in the prestige, you just do this, like I said, take the adjacency matrix. The prestige of one vertex is defined as the sum of the prestige values of the incoming edges. And you can do this little bit of a trick where you just take the transpose of the matrix. It just makes it easier to express this in a vector notation. Okay, so I'm doing this because I want to write just one mathematical expression. And if you look at the matrix algebra, one can show that this whole equation is equivalent across all the v. Now, it's not just for one particular v. If I were to do this computation for every v in one step, this can be written as, the new value is simply A transpose the previous value. Okay. A transpose is simply the transpose of the adjacency matrix. And then one can show that actually, if you want to know the value at the kth step, right, you can expand that, right? So kth step would be, take the previous value, which is the k minus 1 step, and multiply by A transpose, right? Okay, but then I can recursively expand this. So the k minus 1 must have been k minus 2 multiplied by A transpose. So the two A transposes will multiply, it will become A transpose squared, right? So it will be this A transpose, and the next one coming from, so Pk minus 1 itself was A transpose P of k minus 2. So that means this A transpose and this A transpose, they become A transpose squared. And then if you go all the way back, that says that you can start anywhere you want. It's actually just the kth power of the transpose, of the adjacency matrix in a transpose. So this is actually what the main point is, that once you do this, this is called the iterative power approach. And so one can actually prove that essentially you converge to the dominant eigenvector of A transpose. Now the question is, how many people have heard of eigenvectors before? Alright, so some of you haven't, so let me quickly explain what that is, because this is a very, very crucial concept from linear algebra. And this is again, something that one needs to, if you're going to talk about graph analysis and graph methods, this is one of the key things one has to understand, the link between the graph structure and what the linear algebra methods give us. And as I had mentioned that before, the kernel approach. So this is very, very closely tied, and the eigenvalue, eigenvector computation is one of the key concepts that we leverage. So let me explain what that is. So let me start with a very simple, very simple problem, and let's look at what we have. All right. So what is this eigenvector eigenvalue? Now, let me give you a very quick, brief 101, because I think this will help us understand the rest of the stuff. So normally when you have a matrix, let's say the adjacency matrix or any other matrix for that matter. So I'm going to use a matrix. Let's use A. Okay, so this is a matrix, and for the sake of argument, I'm just going to assume for now. Or maybe I shouldn't, because we're going to talk about something else later. So let's assume that this matrix, in fact, let's just say X is a matrix, so that you don't confuse it with the adjacency matrix. X is some matrix. It has n rows and m columns. Okay, so n rows and m columns. So that means this matrix. Should I even, okay, actually let's not worry, because because that's a different, let me just backtrack. So, yeah, okay, fine. So let's just pick a square matrix, because the adjacency matrix is a square matrix, because I can go the other way, because I wanted to link that with another notion called the singular value decomposition. Okay, that's a very key, again, method we use for dimensionality reduction. But we'll talk about that, when we get there. So let us start with A. Okay, so A is what? A is it's an n by n matrix, right? Of course, it could be binary or it could be a weighted matrix. So let's just say it's some real matrix. So we say that A belongs to R n by n. Okay, it's any n by n matrix in the real, it can take any values from the real numbers. Okay, so it's an n by n matrix, and if you take this matrix A, let's pick a small example. Let's say, a 2 by 2 matrix. So let's pick up, and let's pick up a symmetric. So let's assume it's an n by n matrix, and let's assume that it's symmetric. And similar things can be said about asymmetric, but let's just say it's symmetric for now. So let's pick something. Let's just say, so it's adjacency matrix for a graph, right? So I'm going to say that, okay, let's make it 3 by 3. So 1, 0, 1. That means there is a self loop. So let's just not do that. Let's say 0, 1, 1. So okay, let's make a graph first. So there are 3 nodes. Let's call that node 1, node 2, node 3. Alright, so 1 is connected to, so in this case I'm saying 1 is connected to 2 and 3, right? So that's the first, so this is 1. 1, 2, 3, 1, 2, 3. Right? So it's an n by n matrix. So I'm just going to make a binary matrix to make it easy. Okay, now 2 is connected to 1, but 2 is not connected to 3. And there is no self loop, so this is also 0. And 3 is only connected to 1. So 3 is connected to 1, it's not connected to 2, it's not connected to itself. Right? So that would be the adjacency matrix for this graph. So it's just a 0 or a 1 depending on which pairs are connected. So obviously 1 is connected to 2, 1 is connected to 3, so you get 0 and 1. There is no self loop. Okay, so you have a matrix like this. Now, in general, if you take a matrix and you multiply by a vector on the right hand side, okay, so you take the matrix, and in this case, by the way, in this case, because it is symmetric, A transpose is the same as A. Okay, that's what it means to be symmetric. So we don't really have to worry about the transpose part. Normally you would do the transpose, but in this case the transpose is itself because the matrix is symmetric. So I'm just simplifying some things. But nevertheless, so now you take some vector. So let's pick any vector. Geometrically, so what I want to do is, what is the geometry? So what happens is that this matrix actually is going to be in three-dimensional space, okay? Because it has three, actually in this case even a lower rank matrix, but let's not worry about that. But normally, geometrically speaking, if you have a vector, let's call it the vector P, the prestige vector, right? Once you multiply A times P or A transpose times P, this matrix, it will give you something new, right? It's going to give you P prime. Okay, so it's going to give you possibly a different vector P prime. So what the matrix does is, it is actually what is known as a linear operator. Okay? It's a linear transformation. Thus, any matrix you take is basically a linear transformation. So this is a key point that you should keep in mind, that a multiplication of a vector by a matrix is pretty much a linear transformation. Okay, this gives you, in other words, what you get out cannot be a non-linear combination of things. It has to be a linear combination. So a matrix is a linear transformation. So what does that mean? Well, what that means is that you can take that vector, okay, you can expand it, you can shrink it, you can flip it. Okay, so there are only a few things that a matrix can really do, like a linear transformation. It has a precise mathematical meaning, and these are basically the operations you are permitted to do on that vector. So in other words, the resulting vector can be much longer, if you will. It can be in the opposite direction, right? So you can do all those things. Those are the possibilities because of that linear transformation. And normally, when you pick some vector and you multiply by the matrix, you'll get some other vector, because there's no relationship between P and P prime. I mean, the relationship is through that transformation. Basically, you're flipping, you're scaling it, and making it bigger and smaller. But there is a special vector. Okay, this special vector is this eigenvector, which leaves the vector unchanged. In other words, if you take the matrix and you multiply that vector, the only thing you do is you can just, again, the direction does not change. When I say direction, you can only, the only thing that's allowed is you can scale it. Okay? You can make it bigger or smaller, or you can flip it, because you can do negative, you can do a negative value. So basically, an eigenvector is precisely, I'm going to use we use the symbol U. It basically leaves it unchanged except for this constant. So this lambda is called eigenvalue. Okay, it is some scalar value. And I'm going to use the arrow symbol to denote that it's a vector. So U is a vector, and U is the corresponding eigenvector. So in other words, an eigenvector is a very special direction, okay? Which basically says that when you multiply that matrix and that vector, you don't change that vector, the direction does not change. The only thing that might change is the lambda value. You're allowed to make it bigger, smaller, or negate it. And by negation, what happens is that when we talk about direction, here's a vector u, and you multiply, you might get something back, right? You might get -1 times u. So if it's -1, it's just a flipped vector, but it's still considered the same direction. So it's not exactly, maybe a little bit counterintuitive there, but essentially it's just a scalar, change. Now it turns out that there's not just one eigenvalue and one eigenvector. Actually, there can be, for an n by n matrix, there are actually n different eigenvalues and n different eigenvectors, possibly. Okay, so the maximum number of eigenvalues, the maximum number of eigenvectors you can have is n, which is called a full rank matrix. So n, so normally we denote that as, this is not just one equation, this is actually, it's a series of n equations. Okay? So the n equations are, say A transpose ui is equal to lambda I ui. So that means there are possibly n different eigenvalues, eigenvectors, and eigenvalues. Okay, so now we come to the key notion. So there are n of them, okay? That depends on what is called as the rank of the matrix. By the way, in this example, if you remember anything from linear algebra, for those of you who did, there are two rows that are the same, which means that this matrix cannot be a full rank. Okay, the full rank in this case would be 3, because there are 3 rows and 3 columns. So the maximum rank could have been 3. So this one definitely has rank 2. Okay, there are 2 independent, and definitely these 2 are independent. These 2 you cannot obtain by a linear, by a scalar multiple of the other. So in fact, in this case, the rank is 2. So that has to do with how many, so in fact, one of the eigenvalues is going to be 0 in this case. So if you look at the eigenvalues, there will be one would be 0, and the other 2 would be some other value. So anyway, this is all sort of part of the linear algebra, background that one sort of needs to. So I encourage, for those of you who haven't really done that too much, it's a good time to sort of go and, I can have some material to read. This is something to follow up later, to read up on this, because this is one of the key notions, that there can be n different eigenvalues and eigenvectors, but the one we're interested in now is actually the dominant one. Okay? So what we do is we actually arrange them in such a way that lambda 1 is greater than equal to lambda 2 is greater than equal to lambda n greater than equal to, So what we do is we arrange them from the highest to the lowest. Okay, so whenever I talk about lambda 1, I will always talk about the largest eigenvalue. Okay? And then the lambda 2 will be the next. So we can, because they are real numbers, okay, we can sort them from higher to lower. And we can also do the corresponding eigenvector. So the u1 will be the dominant eigenvector, u2 will be the next one, un can be the next one, and so on. And this is really what we really want. So right now, we don't really care about the other n-1 things. One can show that this power iteration method converges to the dominant one. Okay. Now there are some conditions under which it might have problem converging, but as long as there is a clear separation between lambda 1 and lambda 2, you can guarantee more or less. So it's pretty much a very robust computation that more or less you converge to the dominant eigenvector, which is u1, which corresponds to the largest eigenvalue. And that's what the main computation is in this approach. So the prestige, and that's why this prestige is also called an eigenvector centrality. Because essentially all you're doing is you're taking the adjacency matrix and you're computing the dominant eigenvector of the adjacency matrix. So that's the real sort of insight into this, the mathematical sort of property. And this is just an algorithm to show how we can. And later on, I might do a hands-on sort of demonstration of this convergence property when we talk about the hands-on part of the so each one of us can probably implement something like that. All right, so that's that. now we come to the PageRank. So how does PageRank differ? So you have the prestige, okay? You have the prestige. So we should be stopping soon, right? 1:15. Okay, good. So we have time to finish this part. So let's actually talk about PageRank, because this is obviously the sort of the more modern notion. So here we're going to make a few changes. Okay? The first is that if you look at the prestige, the previous course, we were not doing that division by the degree. Okay, so we did not have a probability vector, we did not have a proper transition matrix. So the first thing for us is that instead of the adjacency matrix, I'm going to use the normalized adjacency matrix. Okay, all that does is, instead of A, I'm going to use N. And what we do is we take the weight, or in this case, if it's just a binary matrix, you divide by the out degree of that node. Okay. So let me do a small example here. So supposing the same thing as before. This is 1, this is 2, this is 3. So obviously the adjacency matrix we had from before was 0, 1, 1, 1, 0, 0, 1, 0, 0, right? So now what we have to do is, this matrix I have to normalize it. I have to make it a proper transition matrix. And to make it a proper transition matrix, I have to divide each row by the out degree. So the first row will be divided by 2. The other 2 rows will not change because they are divided by 1. There is only one neighbor. Normally this is done on a directed graph. Okay, so normally we, because the real web graph is directed, there are hyperlinks from one to the other may not point back to you. Likewise, in a social network, you can follow someone, they don't have to follow you, right? So typically this would be directed, so maybe we'll just make it directed. And let's say this is what it is. So it will be a little bit different now, the matrix, and it won't be symmetric anymore. So this would be 1, 2, 3, 1, 2, 3. But it's not very interesting because we don't have, so actually let me add this thing. With directions we can do stuff like this. So okay, 1 points to 2, and that's it, right? 2 doesn't point to anyone, that's the problem. 3 points to 1, and 3 points to 2, and that's it, right? This is actually an interesting case because now we have a thing. In fact, it's good we did this case because in real world this can happen. There are only incoming edges and there's no outgoing edge. You know what those sinks could mean, right? What do you think from an adversarial point of view, what do you think a sink node is?
That is just sending equation.
It's basically, it's like maybe a site with malware, for example, right? So it basically puts all these, 10,000, search, keywords which are hidden on that page. So when you do a Google, this is called link spamming, right? So before this used to be a huge problem, even now it is, where you type something and this page shows up which has no relevance to you. But it will make you click that link and go there, and when you go there it will probably try to download some, some virus onto your computer. So these are like, sync nodes are generally one of the signs of, danger, because why should why should only things be, not the only sign, but if there are many incoming links and no outgoing link, then that's definitely a bad site, right? So it's a malware, a site that is probably serving some malware. So anyway, this is your transition, this is adjacency matrix. So what is the normalized adjacency matrix? It will be 0, 1, 0, because the first row, right, the out degree is 1, so we just divide by that. We can't do anything with this, but the third one has 2, so this will become half and half. So this matrix is called the normalized adjacency matrix. Okay, so now it's every row, except for of course all zeros, every row is what is called as a stochastic probability vector. Right, all the entries add up to 1. So every row must add up to 1. Okay, so this is the first thing that PageRank does. Instead of using the adjacency matrix, it uses the normalized one. And so you could just do the same thing. So you could basically say that I can compute, the PageRank just using that number, right? And here we're going to have a problem. The problem is that as we keep on updating this, the sync node will attract all the PageRank, okay? Because it's called a sync node for that reason, because all the edges are coming in, and the PageRank, so basically that is not a very good thing for us to do. So this is where they also fix that. So they say that actually, technically speaking, what happens in the real world is that people, so this is like saying that, people, when you are surfing at node 3, you can go to node 1, you may go to node 2. If you're at 1, you may go to 2. But what people also do is that people randomly jump from one node, from basically, you might be browsing something, and then you basically lose interest and you jump to some other node, right? So this kind of a random jump is one of the key sort of new things that Google PageRank adds. So it says that technically you can jump from any node to any node in the network. So there is always this virtual backbone. It's a complete graph. Okay? So there is a chance that you would jump from one node to any other node in the web. And we basically treat everyone else equally. So now what happens is that we call this the random part. Okay? So there is a normalized random network. So that network, by the way, in this compact notation, is like saying that I have this network which is all ones. In fact, I can jump to myself. That means I don't jump anywhere, right? So it's like I can also choose to remain on that same node. And then all you have to do is just divide by 1/3. So that's this whole thing is kind of like that. Right? Because it's all 1, 1, 1, 1, 1, 1, 1, 1, 1. I divide by 3, I get 1/3, 1/3, 1/3. So you have a completely equal chance of jumping. So this is also a probability vector. Each one of them is a normalized probability vector. And so what PageRank does is it basically combines these two things. It says I'm going to take the actual structure and I'm going to take this random component and I'm going to combine them in a linear way. How do I combine them? I combine them exactly, like I said, in a linear fashion. Okay? So take alpha times the random part and 1 minus alpha times the regular part. So, and by the way, alpha is some small value. So I pick, this is called the random jump probability. So let's say alpha is 0.1. That means 10% of the time, someone will jump randomly to any other node, but 90% of the time, you will use the actual hyperlink structure. So in this case, it would look like this. So if I combine them, my new matrix M, I'm just going to call this M, will look like this. It will be 0.9 times that 1, 0, 0. No, so what was it? Sorry? It was 0, 1, 0. Half 0 plus 0.1 times 1/3, 1/3, 1/3, and so on, right? So let me write down below. Plus 0.1 times 1/3, 1/3, 1/3. So this is your combined matrix, basically. So that's what essentially Google PageRank is doing, is you have the actual structure part here, and 90% of the time you're just going to follow the hyperlink structure. 10% of the time you're going to do a random jump, and we just combine them into one matrix, and that matrix is called M. Okay, so M is basically a linear combination of the hyperlink structure plus a random component. And so for us, it doesn't really matter. It just says that because it's a linear combination, everything is still a probability vector, it's still a transition matrix, right? It's a transition matrix that takes the transitions, the random jumps into account. And basically that's what you do. Now what you have to do is essentially, you can just compute the dominant eigenvector of this new matrix. So computationally nothing has changed. It's just a different way of computing the matrix. Instead of using the adjacency matrix, I use this normalized matrix with a random component in this, whatever alpha fraction you want to choose. I think normally 90%, 10% is the accepted value. And then you just compute the actual computation is exactly the same as before. It's an iterative matrix vector multiplication. It's a dominant eigenvector computation. And it will converge And whatever it converges to, that vector gives you the PageRank score. So I can extract the PageRank value from that. So I think I have an example here. Let me go to that one. Let's see, do I have it? Yeah, it's here. So this was this network, and this is showing you the efficiency matrix, right? So basically, as you can see, node 1 is only connected to node 4. So you have 1, 2, 3, 4. It's not connected to 5 and so on. So this is the adjacency matrix. This is the transpose of that matrix. Now it's going to be different, right? The transpose is going to be different because it's a directed graph. So then you can do the, this is not showing the PageRank approach, but this is showing you the, the pristine one. But the same idea that you start with the equal score, you keep on updating it, and eventually it converges. And this is what, this is what it comes out to be. So in this small example, it's kind of difficult to see, but node 1, 2, 3, 4, 5, okay, 2, 3, and 5. Okay, so 2, 3, and 5 have equal prestige. So in this example, it turns out that 2, 3, and 5, in the prestige sense, they had equal prestige. I have to check. I should have had that in my slide, but I don't have the PageRank score. But these three are the important nodes in terms of the prestige score. If I don't normalize things and I don't look at the random component, those are the three more. And again, one has to then sort of go back and see, okay, why is it, right? So one can try to explain that perhaps. But the idea that the key point I want to emphasize is that the eigenvector, right, the entries of that eigenvector, they are giving you the actual PageRank score. So that's the key point. All right. So now one last thing, and then we can stop for the morning. So this basically finishes this notion. But this is also very famous. Almost as famous as the PageRank is the so-called HITS score. Okay, this was done by John Kleinberg in Cornell, proposed by him. So this one, this sort of comes really from the web, and maybe it also generalizes to many other applications. But here's the key idea. In the web, for example, if you look at the early days, you have, and even now for that matter, right, you have these what we call hub sites, like Yahoo News or CNN or whatever, right? So they are, Yahoo is more representative of this. So it's kind of like acts as a hub, or in other words, it has many outgoing links to authoritative information. So normally in the web, we observe this kind of a bipartite-like structure, that you have something called a hub node, and a hub is a node that points to other nodes that are good authorities. Okay, they are authoritative on a given topic. So this one has many outgoing links, okay, to these nodes, which are called authority nodes. So for example, Yahoo might say, if you want to find out about education, go to this site. If you want to find out about data mining, go to this site. Right? So it's kind of like a directory kind of a structure. And on the other hand, the authority, so it's kind of like this, this bipartite structure means that if a lot of hubs point to, those pages as being the authority, your authority goes up. So if you have many hubs pointing to you, your authority score goes up. And the other way is also true, that the hub score, the hub score depends on. So we want to compute the two scores. Okay, so authority depends on how many hubs point to me, and the hub score depends on how many good authorities. Right. So the hub is defined in the same manner. That a good hub is it points to good authorities. Okay. So a good hub will point to a lot of good authority nodes, and an authority node has many hubs pointing to it. Okay. So that's the sort of thing we want. Now, this is like the good part, okay? Now let me show you the counter example, which is, or rather the flip side of this. This kind of bipartite structure is also observed in malware networks. Okay, so for example, so let's say online retailers, right? So Flipkart, Amazon, has two examples. So what happens is that you have this community of buyers and sellers. Okay? So in this case, buyers is one side, sellers are the other. And what happens is they're all fake. Okay? And so what they do is the fake reviewer, so to speak, right? They say, I bought from that person and the delivery was on time, you know, great score, everything working out good. So this seller now gets a very high score. You know, they get 99%, you know, in that 5-star rating. But they're all fake because they have the buyers and the sellers are all in collusion basically. So, but they lift up the ranking of that whole bipartite structure. So in a retail network, if you see a bipartite network like this, it's a sure sign of a scam basically. That means the sellers are selling fake stuff. They lure more customers, you know, to buy from them, and at some point they'll just take the money and not ship anything, right? And then they'll repeat this for some other thing and repeat for other thing. So this kind of structure, the fake structures, is a sign of a bipartite structure. Is an example of a bad, you know, sort of criminal networks basically. So they're again both good and bad. So here what we're doing is we are computing two numbers really. Okay. So like a buyer score and a seller score. Okay. Or a hub score and an authority score. So that means there will be two different vectors. So I'm going to call one vector the A vector. And as you can see, the A vector is the same as before. It's pretty much like the prestige. Okay, it's pretty much like the Pagerank. So it says that but except that now I only sort of change the focus. I say, you are a good authority. Okay, if you look at your neighbors and you look at their hub score. So that means if good hubs are pointing to you, your authority goes up. Okay, so this says that authority depends on the hub score of the neighbors. And the reverse is also true, that your hub score depends on how many authorities you are pointing to. Okay? So if you point to more authoritative pages, your hub score goes up. That means you're a reputable site. You're not linking to just random, you know, pages for information. So this is a two set of equations. And it turns out that you can then write them in a very compact manner. Like again, because now every vertex will have two scores. It will have a hub score because we don't know beforehand who's the authority, because no one tells us. So for every page I have to compute, you know, for example, for V, I have to compute what is the authority score of V, what is the hub score of V. Okay, so two numbers or two values will be computed for every node. But then we can express these two numbers as two different vectors. Okay, a vector of length n, which is n is the number of nodes. So I can say that the authority score is the same as before, right? If A transpose, instead of A, it is actually A transpose H, because it depends on the hub score. So we're doing this, we're playing this game of bipartite relationships. And the hub score, the new hub score, is A times, so this is just, you know, comes out of these two equations basically. That the hub score is A times the authority score. But now notice what we can do. You know, this is like one-step expansion. Actually, I can do a two-step expansion. I can say that this H, right, so think of it this way, at the kth step, the authority score depends on the hub score from the previous step, A transpose times the hub score from the previous step. But the hub score from the previous step is actually the authority score from the step times the A vector, okay? And then what we can do is we can regroup these two, so it becomes A transpose A times A of k minus 1. So this is actually extremely important, this A transpose A, okay? This is actually what we call, it's more or less like a correlation, okay? It's more like it's more or less like a covariance actually, the covariance between the vertices. A transpose A is essentially what is called as essentially a covariance matrix. So very much like a covariance matrix. So in other words, if two nodes have similar neighbors, they'll have higher relationships. I'll talk about these things later on again when I talk about the kernels and things. But this is just to keep in mind that it's very similar to a covariance matrix. Because it's going to be symmetric, positive, semi-definite matrix, because those are the properties of being a covariance matrix. But anyway, let's go the other way around. So what about the hub score? The hub score depends on the authority, the adjacency matrix times the authority. But the authority score is actually in terms of the hub score, is A transpose that. So then I can regroup these two. So I can say that the hub score depends on A transpose times HK minus 1. So what is the bottom line? The bottom line is that actually you can now compute the dominant eigenvector. So essentially the point I want to make is that the hub score and the authority score can be computed. This A transpose A is some matrix. It's a square matrix, symmetric matrix. Likewise, this is a square symmetric matrix. So it's just, again, two other matrices. And I can, again, compute the dominant eigenvector for A transpose A and A transpose. And those eigenvalues and eigenvectors are going to give me the dominant, the dominant eigenvector of A transpose A will give me the authority score. And the dominant eigenvector of A transpose will give me the hub score. So as you can see now, this is if there's one algorithm, if I can say, right, that characterizes the domain today, you'll find all kinds of diffusion, problems. They're just eigenvector problems. Okay, you talk about Pagerank, people have talked about profile rank, Twitter rank, this rank, that rank, friend rank. They're all the same. Once you understand this idea, all of this literature is essentially some variation of this. Okay? There's actually fundamentally no real mathematical difference. What is different is, of course, the application. What kind of tweakings you have to do to make it better, right? More personalized, more relevant. But algorithmically, mathematically, there will be very little change from these two. So either you're just doing a pure eigenvector computation of adjacency matrix or some other matrix, or you're doing it for some variation of like A transpose A, A transpose A. So I think that's sort of a good place to stop for today. So let it sink in, and I don't know what the plan is for the rest of the. So we'll do the tutorial later, right? After the lunch. Setup. Good. So more or less. Yeah. And for Python. Actually, iGraph is also available for Python if you want. But this one has a better one that I like better, is actually called NetworkX. So if you can install these two on your machines, then we can, I'll probably use one of these to demonstrate, but depending on which you're more familiar with, you can do some coding. So we want to do the hands-on part. So because I want to sort of go through and show how we can do things. Some of these computations, how to do them in the. Sorry? Yeah, both of them, Windows or Linux or whatever you have is fine. Because we're not going to be here.
Attendance sheet. Hello, tell your name, Mr. Chair, and what you are doing.
I am myself Zaki and I am doing software and Muslim
In which field you are?
Now I am really exploring big data.
Big data analysis.
Actually, should we pause it up? So everyone else will.
Myself, Lalimon Goyal. I am submitted my PhD thesis under Professor Centrality and Professor Pagerank in the Department of Statistics.
I am Abulaish from Iran. I am PhD student in Germany in bioinformatics. I'm doing PhD in Germany. I am doing master in computer science in
I'm Kabe, I'm doing PhD in Abulaish in Pagerank. And my specialty is wireless sensor network. I'm interested in data mining.
I'm Karim Shine. I'm doing MSc Bioinformatics from
I am Taslim Arif. I have done PhD in computer sciences. My topic was social network construction using web mining techniques. I am working as a faculty member at Department of Information Technology in Baba Ghulam Shahbaz University, Rajouri.
I am Mohammad Aslam Parvez. I am doing my PhD from this department, computer science department here at Jammu.
I'm interested in data.
Myself is Fayyaz Ahmed. I am working in Department of Computer Engineering, Jamia Millia Islamia. My area of interest is data mining and big data.
Myself Prashant Giridhar Shamdarkar. I am pursuing my PhD from Computer Engineering Department on data mining.
I am Zohair. I am teaching as a guest faculty in Department of Computer Science.
I am Nashi Nahu. I am doing MTech from CDAC Noida, and my area of interest is data mining.
I am Akash, and I am doing my master's in MSc Bioinformatics from the same department.
I'm Niti. I'm doing MSc Bioinformatics from Jamia.
I'm Chami Saxena, doing PhD from Computer Engineering. My interest is complex network and centrality measures in incomplete information networks.
Myself, Amreen Mohammed. I'm pursuing my PhD in the Department of Computer Engineering, Jamia Millia Islamia, and my research area is cross network-based recommendation system.
My name is Dipali Kampania. I have done PhD from IIT Delhi, working as Associate Professor in the Vekar Institute. My area of interest is data mining.
Good afternoon, myself Meenu Chopra. I am working as an assistant professor in Vivekananda School, and my research area is social media networks.
Good afternoon, sir. My name is Sean. I am a research scholar in the department, and my research team is analyzing gene expression data. So basically, it's bioinformatics too.
My name is Ashok Kumar, and I am pursuing PhD from this department in Leicester. And my research topic is total data mining for figurative language identification and sarcasm.
Greetings, my name is Harshada Dalal. I am a research scholar under the excellence island of Professor Muhammad Abulaish, and my research area is cyber threats.
Myself is Sharon Prof from ELB College, Centrality College, working as associate professor. My PhD was in university, and now I am exploring in law.
Good afternoon. I'm Zaki Saxena, assistant professor at Delhi University, and my current area of research is graph mining and network comparison in biology.
Myself Alka. I'm working at Kansraj College, University of Delhi as an adult, and my research area is X-mining.
Hello sir, my name is Sunil. I am assistant professor in Jamia Millia, and my area is web mining.
Good afternoon, sir. Myself Nazia Mehta. I am doing research in the same department, and my area of research is wireless sensor networks.
Good afternoon, sir. My name is Samya, and I'm pursuing PhD from this very department. My area of interest is big data analytics.
Good afternoon, sir. My name is Anishi Zah. I am doing PhD from this department, and my research area is bioinformatics plus software engineering, combination of all.
Good afternoon, sir. My name is Faraz Ahmed. I am doing research under the guidance of Abulaish, sir, and my research area is social networking science.
Assalamu alaikum. My name is Nisar Iqbalwani. I am working as an assistant professor in computer science in Kashmir University. I am pursuing PhD from Jamia Millia Islamia, and my research topic is gene regulatory networks.
Good afternoon, sir. My name is Sigurd Shadri, and I am doing PhD in this department under Dr. Mr. Palan, sir. And my research area is cloud computing and data.
Good afternoon, sir. My name is Syed Shafat. I am pursuing PhD from this department, and my research area includes data mining and artificial intelligence.
Assalamualaikum, sir. My name is Naeem Ahmed, and I am doing a PhD in the same department. And my area of research is mobile networks.
Good afternoon, sir. My name is Nancy Agarwal, and I am doing PhD from the same department, and I am working on web application security.
Assalamu alaikum, sir. My name is Mohammad Wasid. I am pursuing my PhD from Aligarh Muslim University, Computer Engineering Department, and my area of interest is recommendation system.
And my research topic is soft computing and artificial intelligence.
Assalamu alaikum, sir. My name is Mohammad Fazil. I am doing PhD in this department under Dr. Muhammad Abulaish, My research area is online social network analysis, in which I am working on characterization and detection of social bots in Twitter network.
Good afternoon, sir. My name is Zaki. I am doing PhD from the same department, and area of interest are text mining and data mining.
Good afternoon, sir. My name is Nick Kumar, and I am doing PhD from the same department under Abulaish, and my area is context and trust-aware recommender system.
Good afternoon, sir. My name is Farhana, and I am doing PhD from this department. My research interest is biometrics.
Assalamualaikum sir, my name is Abulaish. I am doing the PhD from the same department on online social networks analysis, and my topic is fake profile detection in social networks.
Good morning. Good afternoon, sir. I am Kashishara Shakil, and I am doing PhD from the Department of Computer Science, Jamia Millia Islamia, and I am working on data management and cloud computing.
My name is Shahab Zaki. I am doing my PhD from Department of Computer Engineering at University. My area of research is behavior analysis and online social network.
Good afternoon, sir. I am Chetna, pursuing PhD from Department of Computer Science. The broad topic of my research is computer-aided drug design using machine learning technique under supervision of Dr. Abulaish.
Good afternoon, sir. I am Seema Rani, and I am pursuing PhD from the same department under Monica Maritana, and my area of interest is in social network analysis.
Assalamualaikum, sir. My name is Nazir Tabasum. I am pursuing PhD from Computer Engineering Department, Jamia Millia, and my area of interest is classic time science.
Assalamualaikum, sir. So my name is Kishu Sudha, and I am a research scholar at this department. And my research area includes information retrieval using classical.
Thank you, sir. I am Fareez Siddiqui. I have done a PhD in semantic technologies and software engineering, and currently I am working at Jamia Millia as well.
From computer science department, and I am a faculty member here. And my research interests are soft computing and pattern image.
Good afternoon. I'm Dr. Monica. I'm associate professor in this department. My research interests are information retrieval, social network analysis, and data mining.
Excellent. So I think this is the right audience. I think the interests are span tech, recommender system, social networks, bioinformatics. So hopefully we'll have interesting things to cover in the coming days. Thank you.
Tomorrow we have very tight schedule, Friday. We have first session from 9 to 10:15, second from 10:15 to 11:30, and there is tea break in between. And last is 12 to 1 p.m. So try to be on time. Try to be here by 8:55.